In this video, we'll be talking about modeling and simulation of walking robots. By the end of this video, you will learn how to model a bipedal humanoid robot using Simulink and Simscape Multibody. We'll start by modeling the three-dimensional mechanics of the robot, including all the rigid bodies and degrees of freedom that make up the system, along with properties such as dimensions, mass and inertia, stiffness, damping, and so on. Next, we'll incorporate the physical contact between the robot's feet and the ground, so that moving the joints of the robot will have some effect on the environment and the robot will actually walk. And finally, we'll explore the trade-offs between model fidelity and simulation speed by looking at different types of joint actuator models, starting from joints that can ideally follow a motion profile and ending at electrical motor models with closed-loop control. So let's start with the mechanical modeling. With Simscape Multibody, you can create 3D rigid body models in two different ways. First, you can create a model from scratch, using known values for mechanical properties such as mass, inertia, and geometric dimensions. Or even better, you can define MATLAB variables for these values so that your model is parameterized and you can later change these values in multiple places as your design changes. The alternative is if you already have a CAD or URDF model of your robot, is to import these models into Simscape Multibody using the SM import function. For this video, we'll focus on the first approach. So let's see this in MATLAB. So once you've downloaded the files, I'm just going to run the startup walking robot script here to get my environment started. And then I'll go into the modeling and simulation folder. In here, there's going to be an intermediate subfolder that has a couple of steps that we're going to go through one by one. So let's start with the first one in which we've modeled the mechanics of the robot. You can see from this model, there are a couple of blocks that are connected together, and they all start here at the bottom left with the world frame, the solver configuration block that is needed for all models using Simscape, and the mechanism configuration block in which you can define things such as the direction and magnitude of gravity. After this, you have a couple of solid objects and rigid transforms that make it all the way to the robot. So I'm just going to zoom into one of the legs here. Let's go to the left leg. So as you can see, the leg consists, again, of a sequence of solid blocks, rigid transformations, and joint blocks. And all of these are going to define that 3D system. For example, if we look at the foot, then this has some information about the geometry. This foot is modeled as a brick solid, and it has dimensions that are defined using some MATLAB variables like foot x, foot y, and foot z, and there are also units associated with these. In addition to the bodies themselves having dimensions, all of the rigid transformations between parts have some kind of conversion as well. For example, this conversion between the ankle pitch to the ankle roll has some rotation about the x-axis of 90 degrees, and if there were some translation, you could also define it here. So this is kind of how you build up that whole system. And most importantly is the articulations or joints. If I go to the Simulink library browser and I scroll down to the Simscape Multibody library, you'll see under joints there are lots of different ones available like 6 degree of freedom joints, Cartesian joints, prismatic joints, revolute joints. These are what define motion or degrees of freedom between rigid objects in your model. And in the case of the walking robot, we basically have a collection of revolute joints that define those motions for the leg. For example, this ankle roll joint here is a revolute joint where you can assign things like targets for initial position and velocity. So here we're saying that the initial angle is given a target of 0 radians, for instance. You can define internal mechanics. This is stiffness and damping, and other things like joint limits, actuation methods, and a couple other things that we'll be talking about shortly. So the idea is that we're just going to put together this model that consists of several rigid parts, and we're going to simulate them. When you run this, you see it opens up the Mechanics Explorer, and this is the visualization window for all Simscape multibody models, where you can follow along the structure of the model using the tree view on the left. For example, I can select the left leg and expand this and select individual parts like the foot, lower leg, upper leg, and so on. So this is a way for you to debug whether your model was assembled correctly, is initialized correctly, etc. So as we said, the initial conditions and other things like the mechanical properties, stiffnesses, damping, mass, geometry, they're all going to dictate how this model simulates as we play this model. So what I've done here now is if you click on this link, it's going to open up a MATLAB app that you can use to set different initial conditions. So for example, like if I set my hip pitch to pi over 2 instead of pi over 4, and maybe I'll decrease the damping by a factor of 10, now you'll see that when I simulate the model, because of the wider initial swing of the joints and the fact there's more damping, then the triple pendulum behavior of the legs is much more chaotic. And of course, I could change this the opposite way. So if I increase the damping coefficients to something bigger like 0.1, then there's much more dissipating energy and the legs will settle down to their resting position much quicker. So all these parameters that we were talking about can be found in the robot parameters file. You'll see different things like the dimensions of the ground plane, or the legs, the feet, the torso, and other values. And you can go ahead and change these and see how that affects your model, as well as things like the initial angles or initial height of the robot torso. Because we want this to be a walking motion, then it's not enough to just let the joint start from an initial position and just swing until they reach resting. You actually want to actuate these joints. So here is where we have saved a mat file called joint angs that contains some data. I'll load this mat file, and you see this contains two matrices called jangs-L and jangs-R for the left and right joint angles. So I'm just going to plot this to quickly show it to you. I'm just going to create a MATLAB plot here of basically the first column, which is the time values of the right leg's joint angles, against the second through last elements. Before that, I'm also going to add a legend so that you can see which plot corresponds to which joint. So I'm going to do some string magic here, and let's see what this plot gives us. So again, here you see that this is our list of joint angles over time for joints 1 through 6 for that leg. And if you want to know how these trajectories are obtained, you can refer to our other video called Model-Based Control of Humanoid Walking, where we go through the design process for coming up with such a walking pattern. But for this video, we'll assume that this is our reference trajectory. So now that we have this defined, I'm just going to open up the second model here called Walking Robot Step 2 Motion. And these values that we're just plotting are passed in as inputs to our model. And these values, as you dig in, for each leg, they are then unpacked into their 6 corresponding elements and actuated into these revolute joints as motion profiles. So when we run this simulation, you'll see in the Mechanics Explorer, if I zoom in, that the walking gait is now executed as those values we provided. Now you may notice one thing, which is that the robot torso is currently pinned to a fixed point in space. So even though we're moving the leg joints, the robot doesn't move. So let's see how we can implement the physical contact, which is key for any legged robot simulation. So starting with release 2019B, Simscape Multibody has these blocks called Spatial Contact Force, which can model contact between solid geometries as what's known as a penalty force. What this means is that the force is represented as a stiff spring with damping that is enabled only when the two bodies in contact are overlapping, else there's no force. So what this means in the context of the walking robot is that when the foot is above the ground, there is no force, and as soon as the feet now start coming in contact with that ground plane, you're going to get that contact force that's going to make your robot model walk. Of course, for the walking motion to propel the robot correctly, so to move it forward as you're stepping backwards, for instance, there needs to also be some friction, and that's going to depend on the normal contact force and the relative speed between the bodies in contact. For this walking robot model, we're creating 4 spheres, one at each corner of the foot, and then we're setting up the contact between each of these spheres and that ground plane. Now, this approach will generally work for any convex shape, though you should be careful not to add too many contact points to your model because that's going to affect simulation speed. So going back to MATLAB, I'm going to open up the third model, which shows contact. And here you see that the model looks the same. If I look at the top level model, one key difference is now that we've added this 6 degree of freedom joint block here. And the reason we've added that is because you want that robot torso to move freely in 3-dimensional space. So 3 degrees of freedom for translation, 3 for rotation. And to constrain the system with that physical contact, we can then go into each of the leg subsystems. For example, let's go to the right leg. And then here you see that I have my foot block, that is the solid block of the foot, 4 spherical solids, and then our spatial contact force. So just double clicking on this foot block and going down to the frames section, here you see that I have created these 4 coordinate frames that are placed right at the middle of that corner point of the foot so that we can put a sphere there, and the same for all the other 4 corners of the foot. These 4 frames are then created as ports that then use a spatial contact force to connect with the ground. Now, for each of these spatial contact force blocks, you'll see that they're parameterized in such a way that your normal force has a stiffness and damping value, as well as the frictional force has what's known as a stick-slip friction model, with is a combination of static friction and dynamic friction. So these parameters are very important in getting the contact right. There's some general rules that you can follow for picking good values for these contact parameters. The stiffness of the spring should be dependent on the weight you're holding up, which you know because it's the weight of the robot, as well as any acceptable overlap between the foot and the ground, for example, a few millimeters, and that lets you calculate that stiffness coefficient, which is the weight divided by the displacement. The damping should then be chosen according to that spring constant so that there aren't too many or too few oscillations in that contact force. Typically, we go at least one order of magnitude below the spring constant, but this rule is not universal, so you should really try different values and see what looks good. And then there's the friction parameters. If you have knowledge about the type of contact, for example, let's say this is a rubber on asphalt contact, you can sometimes look up static and dynamic friction coefficients that are representative of your system. But in general, real physical contact is much more complicated, and this is just a modeling approximation. So you can pick values by hand as we discussed, but if you have any real-world data, you can use techniques like curve fitting or optimization to try estimate these values to better approximate your real system. We can now simulate this model. And now you'll see that because of the contact, our robot is actually walking along the plane. Now, so far we've been actuating a robot's joints using a simplified approach that's known as motion actuation. As you see here, what we're doing is directly providing a motion profile to the joints, and the necessary torque is automatically calculated. To do this, we have to define the derivatives of motion, which we can do, for example, by low-pass filtering the signal using that Simulink to PS converter block. And this prevents infinite acceleration, which you cannot have in this force or torque-controlled system. But particularly if you're building your own robot actuators or designing your own controls from scratch, you don't really have the luxury of having this perfect actuation. And if this is part of your simulation work to design these systems, then you probably want to use force or torque actuation. And that depends on whether you're using this for revolute or prismatic joints. What you're doing here is you're applying a force or torque to the joint that you have to then control yourself to implement some kind of walking trajectory controller. Now, as you start getting into these more detailed models, the level of detail of your physical model, also known as the model fidelity, is going to be an important trade-off between how much detail you want your model to represent versus how fast your simulation runs. And to demonstrate this, we've implemented a few types of actuator variants. In this case, we've used the perfect motion actuation, we've created closed-loop torque controller, as well as a full electrical actuator model. So let's see those in MATLAB. So now I'm going to go to just the main walking robot model. So you can see this in the robot joint controller right up top. If I right-click it and go to the block parameters of the subsystem, then there are three variants that have been set up called motion, motor, and torque, and they are associated with actuator type variable, which can be 1, 2, or 3. And this is something you can just set in the workspace. Now, for convenience, we've created these hyperlinks here that will set these variables to 1, 2, or 3 accordingly. So when I click this motion hyperlink, it's really saying that we're going to use that variant number 1, which is our ideal motion actuation. As you see here with ideal actuation, our controller is just taking the values that we prescribe in motion and just passing them through directly. So there's no controller. And then as far as our actuators go, which are inside of our walk-in robot plant model, if I go, for example, to the right leg, then each of these joints, like the ankle pitch joint, a motion-controlled implementation where under actuation, we're providing the motion by input and automatically computing the torque. So nothing too special there. Now let's switch this over to the second variant, which is the torque plus servo. And let me just quickly update the model. So when I do this, now you'll see that the subsystem shows torque instead of motion. And if I click inside of here, then now I'm using the second subsystem variant, which has PID controllers for both the right and left legs. So if I keep drilling in, then here you'll see that there are 6 PID controllers, 1 for each of the 6 joints. Now, individual PID controllers for each joint is one strategy you can employ, and it's one of the simplest ones because the PIDs are relatively easy to tune, but they don't exploit the fact that the joints are actually coupled and that we have the dynamic model of the robot to design a better controller. But this is a starting point, and we've tuned it so that it works for this example. So now that we have these PID controllers that basically take some combination of the measured and the reference angle, they subtract them to give you an error signal, and then they compute a torque that is passed into joints. Going back to the plant model, then if we go to the same leg, go into the joint block, then inside here, now we're using this torque variant. It looks the same, but if you expand the joint block, then its actuation is now that the torque is provided by input and the motion is automatically computed. And the third variant keeps the same PID controllers. So if I switch over to the motor plus servo, so if I go back to the to my plant model and go to one of the legs, then here now I'm in the motor subsystem. And you see that this now contains an entire Simscape network that models the mechatronic actuators. So I want to run you through what's happening here. First of all, the joint block here is connected to Simscape, particularly Simscape Electrical, in which we're using a DC motor block. And if I click into its parameters, you see that it contains certain elements like the resistance and inductance of the motor armature and an electromechanical motor constant, and on the mechanical side, properties like inertia and damping coefficients. Now, to control the motor, typically what you need is some kind of voltage, but in a realistic system, this voltage is powered by some kind of power electronics. So we're taking our joint command and we're using a couple blocks to convert it into essentially a duty cycle and a direction value. The duty cycle is then going to be passed through this controlled pulse width modulation voltage block that's going to control basically how fast your power electronics are switching. And then the direction is going to be controlling another power electronic system called an H-bridge, which basically denotes whether you want that current to flow forwards or backwards through the motor. Now, even with all these details, if I look at this controlled PWM voltage, the frequency is only set to 1000 Hertz, which is actually pretty slow for these types of systems. And the simulation mode is set to averaged, meaning that we're not actually modeling all of the power electronics, because otherwise that simulation would be even slower at the expense of more simulation detail. But if you actually need to get into the individual switching level, maybe you want to change that simulation mode. So going back here, now that we have these three variants, what we've done is set up a script that can run and compare the simulations with these three different variants using the sim function. And then after setting up data logging for our simulation, we can compare things like, for example, the position of the torso as you move through the walking trajectory, the joint angles, the joint torques, and seeing how close our closed loop controller with our full actuator model matches that ideal motion actuated model. Okay, so if I open up this compare actuator type script and I expand this, then what we're really doing is we're simulating this model with the three different actuator variants using the sim function, and then we're using the tick-tock functions to see how fast each of these simulations ran. And then at the bottom, we're just basically collecting all this information and doing some plots based on our log data. So let's go ahead and run this. All right, so as you can see from the command window, as we move from motion actuation to motor actuation, our simulation gets significantly slower from 5.5 seconds to 43.5 seconds at the expense of adding more detail, of course. If we look at a couple of the plots that came up, so here on the left, I've got my comparison between the X, Y, and Z positions of the torso, and they're not identical, but they follow the same overall trajectory shape, which makes sense because we're sending the same joint commands to the robot, but there are some slight differences. You can see that in the plot on the right, for example, where we're comparing for the hip roll angle, the joint angle at the top versus the joint torque at the bottom. And here's where we can do some zooming. For example, if I hone in on just one of the pieces of the trajectory, then you can see that the hip roll response for the blue line, which is the motion actuated line, it's a pretty smooth curve. And then for the motor or the torque actuated ones, which are the red and the black, there are a couple of other oscillations or blips in the model because of the dynamics. As well, you can also see on the joint torque side, if I zoom in down at the bottom, because the motion actuation is more idealized, there are these big spikes in torque that are not realizable with a real actuator. So you see that as we go from the motion model to the black line, which is the motor model, these spikes are less exaggerated. And that's why you get a discrepancy between the motions. But overall, it seems like the robot is still able to walk and follow the trajectory that we provided. So getting all these parameters for your controllers and your actuators right is actually a very challenging design task. And starting with an ideal motion actuated model can often help you gain some insight. For example, what is the required torque that is needed to move the robot through a desired trajectory? If you look at that plot on the bottom right, we're saying that you basically need to be able to provide something like, let's put a tooltip here, something like 22.8 Newton meters of torque to be able to move this joint. So this is kind of the order of magnitude that you would need to control this particular hip roll joint so that you can size your actuator. So that is an overview of some of the modeling and simulation activities you can do using MATLAB, Simulink, Simscape, and other add-on tools. Of course, there's much more you can do, such as modeling more physical details, whether it means using a more complex and realistic mechanical model from CAD tools, or adding more physical details to your actuator models, like the power electronics we talked about. There's also modeling the physical hardware at greater detail. For example, if you're deploying these controllers to an embedded system, you might need to use a discrete time controller, or maybe other data types that are less precise but more memory efficient, like 32-bit floating point or fixed point data types. And there's also effects that we ignored here, like sensor and actuator precision, noise, or even communication latency, to name a few. And that's absolutely going to affect how your walking robot performs. And lastly, our controllers are very simple in this example. You saw that we used individual PID controllers at each joint, and with that we were discarding knowledge about our model, whose actuators are very much coupled, and that coupling could be useful for designing controllers that are much more efficient. We also worked with a joint trajectory that was already provided, but in reality the robot needs to react to the environment. So besides controlling the joint actuators given some profile, there's going to be other control loops to make the robot follow reference commands like a target direction or turning speed, or even react to disturbances like if your terrain is uneven or the robot is pushed by someone. And finally, there's lots of techniques such as optimization and machine learning that you can use to teach your robot how to walk or how to improve its existing walking controllers. So we cover some of these other steps in other videos. Make sure you download the files for this and other examples. And as always, if you have any questions, feel free to reach us in the resources below. Thanks for watching.